Okay, related rates. Let's consider, this is I think example 1 in the book. So the question is as follows. We have a conical tank that's given like this, and the height is given 10 feet, and the rate of change of the volume of the water in the tank is 9 feet cube per minute. So every minute 9 feet cube increase in the volume of the water. And the question was how fast the water level rises. So they are asking about the rate of change of the height of the water. Okay, so we have a tank, and we are pouring water inside, and then as we pour water, the water level is gonna increase, and this is given, dV/dt is given, and the height is given, 10 feet is given, the radius of this top part is given, and the question is how fast the water level rises. Okay, we are going to do some geometry here, and we will use the volume of a cone. Okay, volume of a cone is base times height over 3. Okay, base area times height over 3. Base area is pi r squared. So this is the water level, right? This is a circle here, and we just say it is unknown, so we put an x here, and Taylor's there's a relationship, geometric relationship with Taylor's. It says x over 5 is equal to y over 10. So this is a relationship, geometric relationship that we can use to get a relationship between y and x. Okay. Of course, the variables here, the y is a function of time. As time increases, as we pour water here, y is going to increase, and x is going to increase as well. X is a function of time as well. As time increases, as we pour water here, the water level is going to rise, and the radius of the circle is going to increase. So x is going to change. So x is a variable that's changing, y is a variable that's changing with respect to time. Of course, the volume of the water is also changing as time goes on. So we have all these changing parameters, and we have a relationship. We can explicitly write what the volume is, pi r squared, volume of the water here, pi r squared, r is x, pi x squared, okay, times height, y, over 3 is the volume of the cone. Now we have a relationship between the volume, x, and y, okay, but we don't have anything in terms of t yet. Okay. However, as you see, v is a function of x and y like this, but that's not a good thing. We want to have y as a function of only one variable if possible, and we want to write y. We want to write v as a function of y only. We can write that by using this Taylor's relationship. Thales bağıntısı in Turkish. Taylor's relationship is x over 5, because you have a triangle here and another triangle here. Triangle inside a bigger triangle. Okay. X over 5 is equal to this height over the total height. This is a rule. Okay, Taylor's rule. If we use that, we can get y. Okay, y is equal to 2x as a relationship. So this y is actually twice of x. As y increases, x is going to increase, but there's such a relationship. So that's good that we have this relationship, because we can write v pi x squared times y over 3. So instead of x, I can write y over 2. Okay, so pi y over 2 squared times y over 3. Okay, so I have a v expression in terms of y only, but I'm interested in dv dt. Take the derivative of both sides with respect to time, because everything is a function of time. On my side I have y cubed something, y over, let's say, y over 2 squared, so it is y squared over 4. 4 times 3 is 12, pi y cubed over 12 is on the right hand side. You just take the derivative of both sides with respect to time, and dv dt is given. dy dt is going to be on the right hand side, and y is equal to 6 feet is given too, and you can find it like this. Okay, that's how you would solve dy dt when y is equal to 6 by using this relationship. Okay. How would you do related rates problems? How would you do the related rates problems? What's your strategy? First of all, the meaning should be clear. Related rates. So we are gonna have like at least 3 variables that are related to each other, and then we just reduce 3 variables to 2 variables and write a relationship. Okay, first we are going to have a relationship between these 3 variables, and we reduce this relationship to 2, and then use what we are given, and take the derivatives of both sides, and then find what it is asked. Let's read this carefully. Draw a picture and name the variables and constants. Yeah, drawing the picture is the most important thing, half of the problem solution. Okay, and then use t for time. Assume that all variables are differentiable functions of t. Okay, write down the numerical information. Yeah, what's the numerical information that's given? Of course they don't write it in symbols. You are going to write it in symbols. Okay, write down what you're asked to find. So are they asking dy dt? Are they asking something else? What type of rate they are asking? Just write it down in terms of symbols as well. And then we are going to write an equation that relates the variables. It's the relationship I told you. Okay, for example, v is equal to, in the previous example, pi y cubed over 12 is the relationship between v and y. Actually, at first it was v, x and y, but we reduced it to y. And then you may have to combine 2 or more equations to get a single equation that relates the variable whose rate you want to the variables whose rates you know. Okay, so that's what we did actually. We reduced the number of variables to 2 at the end. Then we are going to differentiate both sides. Even if this relationship doesn't have t in it, but we know each of the variables, they depend on t, so we can differentiate with respect to t both sides. And then we differentiate, then express the rate you want in terms of the rates and variables whose values you know. Yes, these are going to be given, the values are going to be given, and then we are going to evaluate. We are going to use the known values to find the unknown rate, and we are good to go. These are the steps for related rates. For example, in this question, a balloon is flying up. Okay, there's a range finder here. Okay, of course this is following the balloon, and according to the picture, the question is as follows. The rangefinder is here, the balloon is going up, y is the distance that it's flying up, and as it flies, this degree theta is increasing, is changing, right? And we are given the rate of change of this angle with respect to time is 0.14 radian per minute when theta is equal to pi over 4. That's given. Okay, and they're asking what's the rate of change of y with respect to time. So can you find the rate of change of the height, okay, or vertical distance that it is traveling when theta is equal to pi over 4? That's the question. And we are also given this is the starting point of the balloon, and this is the rangefinder position, and this is the distance. This is also given. Thanks God. So we have a right triangle. That's good because we have the Pythagorean theorem. Square of this times y squared is equal to this distance, and we can get a relationship using that. Or we can actually, maybe we don't need this distance, we can just use tangent theta relationship. It's the best. Tangent, because we are interested in a relationship between theta and y. So tangent theta is equal to y over 150 meters. And then, so you take so we have a relationship between theta and y, and both theta depends on time, because as time increases, theta is going to get large and large. And as y is a function of time, because as time increases, the height of the balloon is going to increase as well. The distance from the ground is going to increase. So tangent theta is equal to y over 150 is a good relationship. We set it up and take the derivatives of both sides with respect to t, and the derivative of tangent is secant squared theta and times d theta dt. This is the chain rule we use. It's equal to dy dt over 150. Okay, then we put in the variable known things. So we said that secant squared theta times d theta dt is given 0.14 radian per minute. We put it in, and theta is pi over 4, and secant squared is 1 over cosine. Cosine pi over 4 is 1 over square root of 2, okay, and square that 1 over 2. On the left hand side we have everything in hand, and on the right hand side we have only dy over dt times 1 over 150. So dy dt is equal to 150 times the left hand side, right? So it's how we find it for this situation. Okay, there's another problem. This is an example 3 in our book. Let's say we there's a car that's traveling. Okay. What's the question? So whenever the location, okay, x is the location of the car, and y is the location of the police car. Okay. Okay, the car is probably going away from the police car, and okay, we have this right triangular situation here, and the police car is going downwards towards south. So dy dt is negative 60 meter per second, okay, the speed, and dx dt is going towards the east, so it's a positive velocity. They're asking about the dx dt. We are also given the distance between police car and the car that's police car is chasing, and the distance is s, and the SD, the rate of change of the distance between the two cars, is 20. Alright, and it's also given. Alright, so we have x is 0.8, y is 0.6, and s is going to be then 0.10. Let's see, just a second. S will be 1, I'm sorry, I think. Okay, it should be, and we find s like that, and we can also have the relationship x squared plus y squared is equal to s squared, and x depends on t, y depends on t, s depends on t. We take the derivatives of both sides with respect to time, and then we have 2x dx dt plus 2y dy dt equals to 2s ds dt. I'm going to cancel all the 2's. X ds dx dt plus y dy dt equals to s ds dt, and then I'm going to put everything in. I know x, I know y, I know dx, I know dy, I know ds dt, and from there I can find dx dt. Okay, that's how you would do that. Alright, I'm going to skip this example. Okay.